Hello and welcome to part 2 of section 9.2. Here we will be talking about type 2 error and the power of a test. So the significance test that we are looking at in this section is a 1 proportion z test, and this is an example that we'll be focusing on today. So pause the video and read this example. Ultimately, we have a truckload of potatoes and they are being delivered to a potato truck producer, and the truckload of potatoes needs to have less than 8% of the potatoes that have blemishes in order for the potato chip producer to accept the truckload. If it has more than 8% blemishes, then you're going to send the truckload back to where the potatoes came from. And the way they're going to do that is they're going to take a simple random sample of 500 potatoes from the truck, and when they did that, it revealed that 47 of the 500 had blemishes. We're going to carry out a significance test at an alpha level of 0.05 to decide whether we should accept the truck or reject the truck. Our null hypothesis is that P is equal to 0.08, P being the proportion of the potatoes in the shipment with blemishes. The alternative is P is greater than 0.08, because if it is greater than 0.08, then we're going to reject this truck. If there is not enough evidence to say that P is greater than 0.08, then we're going to allow this truck into our factory. We're going to choose an alpha level of 0.05 because that's what they told us to use. And you can see I wrote a sentence that tells you what P is. P is the proportion of potatoes in the shipment with blemishes. In our in our planning section, we are going to name the inference test we're going to do, which is a 1 proportion z test. We're going to check all 3 conditions. This was a random sample of 500 potatoes. We are going to check our 10% rule. We are going to assume that there are more than 5,000 potatoes in this shipment. And then our large count condition, we're going to do 500 times 0.08 multiplied by 500 times 0.92. Both of those values are bigger than 10, so it's safe to use a normal calculation because our sampling distribution will be approximately normal. Okay. In the do section, your textbook loves to do things using doing things by hand. Again, all we need is the test statistic and a p-value. So you'll see all this work a lot in the answer keys, but all I need is this 1.15 and then a p-value of 0.1251. So let's just do it on our calculators real quick so we can show this again. So in our calculators, we are going to do a 1 prop z test, which is in all of our tests, which is in stat. So if we go into stat and go over to test and go down to 1 prop z test, which is what we're doing, our p naught is 0.08. That's our null hypothesis. And I believe this was 47 out of 500. And we only cared about the right tail, so greater than p naught. And then we hit calculate. And we get this z-score and this p-value. Now, they did it by hand. You're going to use a calculator, and you're going to write those 2 things down in your do section. Okay, so in our conclusion, we have to do 2 things. Compare our p-value to alpha. So our p-value is 0.125. That is greater than our alpha of 0.05. We're going to fail to reject our null hypothesis. There is not convincing evidence that this shipment contains more than 8% blemished potatoes. Okay, we're not saying that we know for sure that there's less than 8%. We're just saying we don't have evidence that there's more than 8% blemishes. Therefore, the producer is going to allow the truckload of potatoes into the potato chip factory because we don't have enough evidence to reject this truck. Okay. Now, that is a 1 proportion z test. Today, we're going to focus on what's called the power of a test and type 2 error, and we're going to be using this example as we move forward. So looking at this situation, what is the cutoff p hat value between rejecting and failing to reject. Like what p-hat value would have caused us to reject this truckload of potatoes? Let's look at this in this scenario. So our sampling distribution was centered at 0.08, and there's some value over here. There's some value p hat that to the right we would have rejected our truckload, and to the left we would have failed to reject. So I'm going to say FTR, failed to reject, which means that we're going to allow the truck to come into the potato chip factory. So the question is, what is this value that is the cutoff between failing to reject and reject? Well, we know our alpha was 0.05, yeah? So that means that this area over here is 0.05. So if we did inverse norm, right, an inverse norm, and then we have area to the left is 0.95, the mean is 0.8, and the standard deviation would have been 0.08, and the standard deviation would have been the square root of 0.08 times 0.92 divided by 500. This would give us this p-hat value, the cutoff value between rejecting and failing to reject. And this p-hat value in inverse norm is 0.099. So if we got a sample that had more than 9.9% blemishes, it would have fallen in this region and we would have rejected our null hypothesis. Our p-hat value that we got was like 0.092. It was 47 out of 500, which falls like right here. And that's why we failed to reject, because it was to the left of this cutoff value between rejection and failing to reject. Why is that value important? Well, we're going to need it because in order to find type 2 error in the power of a test, we're going to need that cutoff value. Type 2 error occurs when we failed to reject the null hypothesis, but we should have rejected it. In our scenario, a type 2 error would be that the truckload of potatoes does have more than 8% blemishes. However, we failed to reject it, so we allowed the truckload into the potato chip factory. Now, there are many values of a parameter that make the alternative hypothesis true, right? Anything bigger than 0.08 makes the alternative hypothesis true. 0.081, 0.085, 0.0810, right? So we are trying to concentrate on just one value, okay? The probability of making a type 2 error depends on several factors. Let's go back to type 1 error. Remember, the probability of a type 1 error is alpha. Whatever we choose alpha to be is the probability of type 1 error. Type 2 error is different, okay? One of the factors is the actual value of the parameter. A high probability of type 2 error for a specific alternative parameter means that the test is not sensitive enough to detect the alternative. Okay? This is called the power of a test. The power of the test is the probability that you will successfully reject the null hypothesis. So again, the power of a test is the probability that you successfully reject the null, meaning that you do reject the null when you should reject the null. The power of a test is the complement of the probability of type 2 error. Okay? The power of a test is the complement of the probability of type 2 error. So if you can find the probability of type 2 error, then you can find the power of a test. So let's go ahead and find the probability of type 2 error and power. So here's our example. The potato chip producer is claiming that 0.08 or 8% of the potatoes have blemishes. Anything bigger than that, they're going to reject the null hypothesis. So let's say that the truck driver coming in knows that the truckload has 11% blemished potatoes. Now, he doesn't want to have to drive all the way back to Idaho to get a new truckload of potatoes. So he's just hoping and praying that these data analysis commit a type 2 error. Because he knows that his truckload should fail the test. But if a type 2 error occurs, then the truckload will be allowed into the potato chip factory. So in this case, the parameter is actually 0.11. But when we're doing the actual inference test, we always assume that the original parameter is correct, which is 8%. So this is our sampling distribution. If the p-value, if p was actually 0.08 and centered at 0.08, we found our cutoff value of 0.0999 that we showed before using inverse norm. Anything to the right of this, you're going to reject the truck. Anything to the left of this, you're going to fail to reject, aka you're going to allow the truck to come on in. If you got a p-hat value over here, when really this was the center, then that is a type 1 error, right? Because if you got a p-hat value over here and this really was the center, 0.8 really was the center, that would be rejecting the null when you should have failed to reject. That's type 1 error. That's 0.05. Okay, that's alpha. Really, the distribution looks like this. Boom. Right? Here's 0.08 center, but that's not the real center of my sampling distribution because we are testing it against 0.11 because the truck driver knows that 11% of the potatoes have blemishes. So the true parameter is 0.11. So this is the actual sampling distribution. Centered at 0.11. This is still my cutoff value. Doesn't change. Right? My cutoff value doesn't change. So I'm actually taking a sample from this truckload. Assuming that it's this truckload. Hoping that my sample will detect that it's really this truckload so that I can reject the null hypothesis. So the question is, what is the probability of getting, of failing to reject, which would be getting a value over here, when I should have rejected, which is getting a value in the gray area. That would be the probability of type 2 error. Okay? So the probability of getting a value on the left side of this green line, which is less than 0.0999, on this sampling distribution is actually 0.2483. That is the probability of type 2 error. Because this would be failing to reject this, but really this is true. So that means the power of the test would be 0.75. There's a 75% chance of successfully rejecting the null hypothesis if the parameter is actually 0.11. This probability will change if the parameter is different, right? If the proportion of blemishes was actually 0.10, then this would change because my center would now be at 0.10, not 0.11. Okay, how did I find this value? I'll show you. Okay, so we have a whole different distribution now. Our task, right, type 2 error in this case, type 2 error is the probability of getting a p-hat value less than 0.0999, which is our cutoff for rejecting and failing to reject, which is just norm CDF, lower bound something small, upper bound 0.0999. My mean is now 0.11 because that's the actual parameter, and this is my standard deviation, 0.11, 0.88 over 500. Now this is the probability of type 2 error. This is the probability that I get a p-hat value where I'm going to fail to reject, but really I should reject it because this is the actual parameter. And 1 minus the probability of type 2 error is called the power of a test, which is the probability that you successfully reject the null. And this would be the probability that p-hat is greater than 0.0999. So this all comes from the cutoff value of where I'm going to reject versus where I'm going to fail to reject, which is norm CDF, lower bound, upper bound, mean standard deviation. So this can be calculated by doing this, which is the probability that you get a p-hat value greater than 0.0999, which means that you would successfully reject the null, or you can do 1 minus type 2 error, which is this right here. And that's what this picture is showing us. Okay, so that means we would successfully or correctly reject the shipment about 75% of the time if P was actually 0.11. Okay, so type 2 error and probability we call type 1 error alpha, we call type 2 error beta. So therefore the power of a test is 1 minus beta, because 1 minus the probability of type 2 error. That's it. See you guys soon.